The wind patterns across the globe reveal why certain regions are ideal for wind energy, with the Middle Plains of America hosting the highest concentration of wind turbines in the country due to consistently strong winds. More wind translates to more power, but one small island off the mainland of Europe stands out as a wind energy paradise: Ireland. Its exceptional wind speeds make it a prime location for harnessing this renewable resource. During one powerful storm, wind energy powered the entire country for 3 hours, and it's not uncommon for wind to supply the majority of Ireland's power on any given day. This natural resource holds immense potential to transform Ireland's energy future, but integrating wind energy into a small, isolated island power grid presents significant logistical challenges. Mismanaged wind turbines can destabilize a power grid, with issues ranging from power storage to grid frequency stabilization. To understand these challenges, we need to examine the engineering marvels inside wind turbines and how they function. At the heart of a wind turbine's nacelle lies a complex system designed to convert the slow, high-torque rotation of massive turbine blades into usable electricity. The blades typically rotate at 10 to 20 revolutions per minute, far too slow for a generator, which requires a shaft spinning at around 1,800 revolutions per minute to produce electricity efficiently. To bridge this gap, a gearbox is employed. These gearboxes operate in stages to transform the rotor's motion. The first stage uses planetary gears attached directly to the blades, increasing rotational speed by a factor of 4. Planetary gears are ideal for this task because their multiple contact points distribute the high torque load across more gear teeth. A second stage of helical gears multiplies the speed by 6, and a third stage increases it by another factor of 4, achieving the 1,500 to 1,800 revolutions per minute needed for the generator. These 15-ton gearboxes, designed for a 20-year lifespan, are a critical component but often fail within 7 years, requiring extensive maintenance. Replacing a gearbox in a wind turbine is far more complex than in a car, as it involves teams climbing over 50 meters to service multi-million-dollar equipment. Harsh conditions, such as extreme wind gusts and salty air in offshore turbines, further elevate maintenance costs, which can account for nearly 20% of the levelized cost of wind energy. Despite these costs, wind remains a cost-effective energy source overall. The precise reasons for gearbox failures remain elusive, but small cracks, known as white etch cracks, form on bearings surrounded by pale, damaged material. These issues worsen as turbines grow larger and more powerful, requiring additional gear stages to handle the immense torque from larger rotors. One solution to bypass gearbox maintenance is to eliminate the gearbox entirely by using a direct drive system, where the blades connect directly to the generator. However, this requires a different type of generator with a large diameter and many magnetic poles to produce the correct output frequency at slower rotational speeds. A single revolution in such a generator passes through multiple alternating magnetic fields, increasing the frequency to match the grid's requirements. The largest wind turbine ever built, the Haliade-X, employs this direct drive system, featuring a 10-meter-wide rotor disc with 200 poles, weighing 250 tons. However, these systems rely on permanent magnets made from neodymium and dysprosium, rare earth metals largely controlled by China, which introduces risks due to fluctuating material costs and trade uncertainties. Ireland is testing these direct drive turbines at the Galway Wind Park, where the massive blades required lowering a road under the Latalia rail bridge to transport them from nearby docks. Evaluating the long-term benefits of such technologies takes years, but as turbines grow larger and more expensive, direct drive systems become increasingly attractive. The next challenge is ensuring the electricity generated matches the grid's frequency, especially since wind speeds constantly vary. For a generator to output the U.S. standard 60 Hz, a rotor with 4 poles, 2 north, 2 south, must rotate at exactly 1,800 revolutions per minute. Any mismatch in frequency can destabilize the grid, potentially causing widespread outages. Grid frequency management is a constant task, as demonstrated in the UK, where operators monitor events like popular TV shows to anticipate sudden demand spikes. such as when viewers simultaneously turn on kettles during commercial breaks. These spikes can lower grid frequency if supply doesn't increase accordingly. A mere 1 Hz deviation can cause significant damage, as seen during the 2021 Texas freeze, when the grid nearly dropped to 59 Hz, risking a months-long blackout. While wind turbines were partly blamed, natural gas plants also failed, and Texas's isolated grid, which avoids federal regulations, exacerbated the issue. Wind turbines are non-synchronous, meaning they cannot directly raise grid frequency when it drops, unlike traditional power plants with large rotating turbines that provide inertia to stabilize the grid. Early wind turbines were designed to spin at a constant 1,800 revolutions per minute, with blade tips moving 7 times faster than the prevailing wind and stalling in stronger gusts to maintain speed. This passive control allowed direct grid connection but subjected the drivetrain to fatigue from sudden torque increases. Modern variable speed turbines address this by using massive bearings to adjust the blade's angle of attack, actively controlling speed. However, this creates variable frequency output, which cannot connect directly to the grid. To solve this, the power passes through 2 inverters. A rectifier converts the variable AC to DC, and a second inverter converts DC back to AC at the correct frequency using electronic switches. This process, while effective, results in some energy loss and disconnects the turbine's inertia from the grid, reducing its ability to stabilize frequency during sudden demand spikes. This lack of inertia is a critical issue for renewable heavy grids, especially as traditional inertial sources like coal and nuclear plants retire. Ireland has tackled this with an innovative solution. In 2023, it installed the world's largest flywheel, a 120-ton steel shaft spinning at 3,000 revolutions per minute in a vacuum to minimize friction. Located at a former coal plant with existing grid infrastructure, this flywheel takes 20 minutes to reach full speed, but can instantly supply power at the precise 50 Hz needed for Ireland's grid. It provides essential inertia for frequency regulation, but Ireland will need 5 more such flywheels to meet its climate goals as wind energy expands. These flywheels are not designed for long-term energy storage, only for short-term grid stabilization. Ireland's isolated grid, with limited interconnections to other countries, poses another challenge. Larger, interconnected grids are inherently more stable, allowing energy trading to balance supply and demand. In an ideal scenario, Ireland could export excess wind energy to France and import nuclear power when winds are low. Currently, Ireland relies on 2 interconnections with Great Britain and has none with mainland Europe, though a planned 700-megawatt interconnection with France could supply 17.5% of Ireland's 4,000-megawatt average demand. This would reduce the need for redundant natural gas capacity and encourage further wind investment by providing an export market for surplus power. Long-term energy storage is another hurdle. Ireland currently has 1 gigawatt-hour of storage, far below what's needed. The government's national hydrogen strategy aims to address this by developing a green hydrogen economy for storage, transportation fuel, and industrial heating. With abundant fresh water from its rainy climate, a strategic location along global shipping routes, and a major airline hub, Ireland is well positioned to become Europe's leading green hydrogen producer. Ireland's push for net zero emissions by 2050, mandated by EU law, aligns with its economic interests, given its reliance on costly fossil fuel imports, exacerbated by global events like the war in Ukraine. Transitioning to a renewable-based economy could enhance energy security and economic growth, leveraging Ireland's wind and water resources to become an energy-rich nation. The shift from trading physical commodities like oil to intangible assets like stored electrons is transforming the energy market. Private battery storage units, which buy electricity when wind is abundant and sell it during high-demand periods, rely on algorithms analyzing weather and consumption data, a form of energy commodity day trading. This emerging sector highlights the growing demand for skills in programming, data analytics, and algorithms, fields accessible through platforms like Brilliant.org. Brilliant.org offers courses to develop these skills, such as Python programming, large language models, or math refreshers for differentiation and integration. These tools are practical for analyzing data, like YouTube Analytics, to uncover trends for better decision-making. With a 30-day free trial at brilliant.org/reengineering and a 20% discount on an annual premium subscription, users can explore these skills to navigate the evolving energy landscape and beyond.